We'll start today's lecture with some of the standard limit theorems that we'll be needing for this part of the course. So this part, what we are converging now, is essentially the asymptotics of Markov chain. And then for that, we'll need some standard limit theorem. So let's just recall them quickly. Okay. So first thing is what is called the monotone convergence theorem. So by the way, this slide and the next slide falls under the following realm, is that if xn converges to x in some sense, say almost surely, the strongest possible sense. So if you have a sequence of random variables xn that converges to x almost surely, under what condition will expectation of xn converge to expectation of x? So this is the question. Now there are various sufficient conditions. One is obtained from monotone convergence theorem, which says that if the sequence is of non-negative random variables and it increases to x almost surely, then expectation of xn increases to expectation of x. Of course, if xn increases, expectation of xn also has to increase. The point is the limit is expectation of x. Okay. One thing that I'd like to point out here is that in MCT, in monotone convergence theorem, the random variables are allowed to have infinite mean. One special case would be, it's possible that all the expectation of xn's are finite, but expression x is not finite. So x has infinite mean. In this case, expectation of xn will just increase to infinity. So this is also allowed in this situation. Okay, one corollary that we have already used actually in this course without properly stating the result, but I think now it's a time. I've already told you that expectation of a sum is sum of expectation. This is true for finite sum, of course, but for infinite sums also it will be true provided the random variables are non-negative. So expectation of an infinite sum is equal to the infinite sum of expectations. This is true whenever you have a sequence of non-negative random variables. This we have used a couple of times, maybe more, okay? We had expectation of sum of indicators, and then we have taken them as sum of expectation of indicators, and then hence we got it as sum of probabilities. We've used it now and again. So this is because of MCT. So the way you prove it is that you just apply MCT on the partial sum. Since all the yi's are non-negative random variables, these xn's are also non-negative random variables which actually increase to the sum of yi's, the infinite sum of yi's, and then use MCT on that to get to this result. Now note here also it's possible that here also the yi's may have infinite expectation. In particular, it's possible that each yi has finite expectation, but the sum of yi's doesn't have a finite expectation. In that case, both sides would be just infinity. Okay. Then another theorem that ensures convergence of expectation whenever xn converges to x is what is known as the dominated convergence theorem. In this case, suppose xn is a sequence of random variables that converges almost surely to x. And in absolute value, each xn is bounded by a random variable y, which has finite mean. Okay, actually expression of mod y should be finite, but in this case, y has to be non-negative, so it doesn't matter. This mod is redundant actually. So this is, in this situation, you can say that expectation of xn converges to expectation of x. In fact, you can say even more. You can say that the absolute difference between xn minus x, this expectation converges to 0. Obviously, this will imply this because the absolute difference between these two can be bounded by this guy. So therefore, this is the strongest statement. So a special case of this would be, this is the form which we'll be using most of the time in this course, that if you have a sequence of random variables that converges to another random variable almost surely, and you have a uniform bound on all the random variables. So all the xn's in absolute value are bounded by some positive number n. Then expectation of xn converges to expectation of x. This is the form we are going to use the dominated convergence theorem. And this form is also known as bounded convergence theorem. Now, the strong law of large numbers, this is the classical strong law of large numbers, which we'll be using today itself. So if you have a bunch of IID random variables with finite mean, then the sample mean, which is x1 plus x plus xn by n, this converges to mu almost surely as n goes to infinity. So this says that for a large sample, the sample mean is a very good approximate for the population mean. That's all this means. By the way, this statement just means that with probability 1, the sample mean converges to the population mean. So the event that the sample mean converges to probability to the population mean, this has probability 1. Okay? Another version of this that is useful, and it will be useful for you in one of the exercises today, is that if xi's are non-negative with infinite mean, okay, xi's are IID, but they are non-negative with infinite mean, then it can be shown that the sample mean actually converges almost surely to infinity. This will be useful for you in one of the exercises that I would give you.